Good afternoon. Before we start, I just want to point out that you have come to the correct presentation. Icebergs. We're going to talk about bioretention icebergs today. Over the next 8 minutes, we'll uncover what's happening beneath the surface of these low-impact development techniques, or LID systems. More specifically, we'll be covering our year-long field evaluation of the performance of multiple bioretention systems in reducing phosphorus loads in urban stormwater. Hello, my name is Nick Moken, and I'm the president of Crozier & Associates in Toronto, Ontario. And today I'm joined by our research partner, Dr. Claire Robinson, who is an associate professor in the Department of Civil and Environmental Engineering at Western University in London, Ontario. Deteriorated water quality as a result of excess phosphorus can lead to toxic algal blooms like the one we see here in Lake Erie back in 2017. The focus of our research is in the evaluation of phosphorus removal from urban runoff. Good data is essential in advancing our understanding of these bioretention systems and for optimizing them for future applications. In order to improve the design and performance of bioretention systems in reducing phosphorus loads, we feel it's important to understand how they're performing today in the field. It's also important to understand the various processes that regulate phosphorus removal, all of which are critical to the pursuit of optimizing bioretention media for future applications. The basic components of bioretention media listed in CBC's guidelines here in Ontario include a topsoil or mulch layer at the planting surface, subsurface media that includes mostly sand, some fines and organics. A layer of gravel is also recommended to promote infiltration into the native soils. Depending on the supplier of this material, the installation contractor, and the inspection protocols, we actually found that the bioretention media in the field that we've uncovered in the field varies considerably. Our study examines the performance of bioretention systems in operation today. 3 of the sites are in the London area in Ontario, and the other 3 sites are in the Greater Toronto area. All include a mix of residential and commercial developments. The field activities occurred during the summer of 2019. Sediment cores, as you see here, were taken from each cell and brought back to the lab for physical and geochemical examination. Rhizon samplers were then installed at varying depths to allow us to analyze pore water characteristics throughout the cells. And now I'll hand it over to Dr. Robinson.
Thanks, Nick. So before I jump into the results, phosphorus behavior in bioretention cells is governed by a number of complex abiotic reactions as well as biological processes, as you can see here in this diagram. We need to understand the relative importance of these different processes and reactions if we're going to be able to enhance bioretention cells for phosphorus removal. So part of this study is trying to understand how we can enhance the removal processes in these systems. And rather than just considering bioretention cells as black boxes and measuring the influent and effluent, we're trying to also understand what's happening within the pore water and the sediment so we can better optimize these systems for phosphorus removal. Looking at the results for the 6 systems that we monitored in the field, here we have the SRP concentrations, which is a soluble reactive phosphorus or the inorganic form of phosphorus for the 6 cells in the influent road runoff and the average concentrations in the pore water for the 6 cells over multiple rain events. We can see that 5 of these systems provided some level of phosphorus removal, with the pore water concentrations being lower than the influent road runoff. The final cell here, however, the Kennedy site, is what we consider to be a failing system with respect to phosphorus removal. And in actual fact, the media here is acting as a source of phosphorus, with the pore water concentrations orders of magnitude higher than the influent road runoff. These pore water concentrations, and as a result the effluent concentrations, are also considerably higher than what triggers eutrophic conditions. And we can also see that's the case for a number of these other systems as well, indicating that if we're going to use bioretention cells for phosphorus removal, we need to be doing a better job at enhancing the phosphorus removal processes. So looking more closely at the soluble reactive phosphorus depth profiles within these systems, here we have these depth profiles for Dorchester, one of our functioning systems with respect to phosphorus removal, and the Kennedy system, which is our failing system with respect to phosphorus removal. Interestingly, what we can see is highly variable SRP concentrations with depth. And while there's a common consensus that phosphorus is often increasingly removed with depth in these systems, we see this isn't the case. For both these systems, as well as other systems we monitored, we see that due to a change in pH and redox conditions at depth, we actually see release of phosphorus at depth. And this highlights the importance of really understanding the geochemistry conditions all the way through these cells if we're going to have good phosphorus removal within the systems. We can also see, importantly, for the Kennedy system, our failing system, how the large SRP release actually occurred within the top 10 centimeters. And this shows the importance of understanding what's happening on the surface of these systems, whether you're applying topsoil or mulch, or what the infiltration capacity is, as this can govern the overall net performance of the systems. We found that pH was one of the major controls on SRP removal for these systems, with the Kennedy system, our failing system, having high pore water pH compared to the other cells. In fact, here, the pore water pH was more alkaline, and these conditions promote release of SRP due to the desorption of phosphorus from available sites, absorption sites. So we need to be considering the pH for phosphorus removal. One of the reasons for the Kennedy site we see such high pH is partially due to the sediment composition. So we can see for the Kennedy site, our failing system, that we have much lower permeability media. What this means is you get less infiltration, longer residence times in the system, and that promotes organic matter decomposition. You get a higher pH, you get lower redox conditions, all factors that promote SRP release. So while we often think about the sediment composition being important for infiltration through these bioretention systems, our field data shows that it's also really important if we're going to use these systems for phosphorus removal. With respect to the next steps, we're now moving from the field back to the lab, taking media from our sites to better understand the different processes governing phosphorus removal in the bioretention cells. We're going to optimize this media and then take the optimized media using different amendments to new development sites for testing. So with that, we'd like to thank you for listening to our presentation. And we're happy to answer any questions that you have.